So, hi everyone, I'm Mary and I'm here to talk to you today about using SAIL to generate a GNU assembler, disassembler simulator for the RISC V toolchain. A little bit about me to start. I'm just an undergraduate student studying at the University of Surrey for electronic and electrical engineering. I'm a UK ESF scholar with Embecosm, and I am the group chair for the RISC V Foundation's open source and university outreach task group. So you all qualify to be in that task group, so please come join us. And if you're interested, come talk to me after this presentation. So in the past, creating a new processor has consisted of defining a formal specification and then creating an assembler and compiler toolchain definition from this by hand. The operation of the assembler and compiler can only be verified once the processor has been manufactured, which introduces a linear dependency. The time scale could be significantly reduced if the definitions could be generated automatically from the specification, but this has proved difficult in the past. However, advances have been made with the processor specification language and framework to generate the assembler and compilers, so it should now be possible. That's where my final year undergraduate project comes in. It aims to develop code in a functional programming language that creates the main file required by the toolchain generator from the processor description with minimum human interaction. The RISC V architecture, more specifically RV64I, will be used as the model. This would represent a significant step towards a complete framework for the automation for automatic translation. During this presentation, I will discuss the processor specification language, SAIL, show a handwritten RV64I example of SAIL, do a little bit of OCaml, and then finish off with CGen, the CPU tool generator, and another example of RV64I, but this time for CGen. So to start off with, I'll give a little bit of context as why I believe this project to be important. A processor is a key component in any computer, which uses logic circuits to perform user-specified operations on data or operands. New processors are being designed all the time to fulfill different area needs, such as low-power processors for wearable tech, or high-performance graphics processors. To allow these modifications, often processors have different blends of hardware and software, which require using special optimizations and new instructions. There are some key steps in the development lifecycle of a processor. These are designing the physical hardware for the processor, defining the processor's optimizations, writing the ISA, creating the simulator of the ISA, running pre-silicon tests, which is basically where you take the ISA simulator and the hardware model and run them together, and then finally manufacture the design. But designing a processor from scratch takes too long and is too expensive. ARM estimates that it takes about 300 engineer years to complete a new reasonable design. So often there is a need to use third-party designs such as ARM or an open source design such as RISC V. Once an ISA is defined, the next step is to write the assembler and disassembler and the other CPU tools. This step is the one that stops many organizations from going down the custom processor route, as it takes a long time and there is no guarantee of success. but it can be done with an open source CPU generating tool called CGen. But this leaves the problem of converting the hardware design of the processor to CGen. Until recently, there was a lack of formal methods to define the hardware in such a manner that automated analysis could be performed to confirm that the design actually does what is required. SAIL was developed to fulfill this niche. The formal model is written in SAIL, a language describing the instruction set architecture semantics of a processor. It is a work in progress by the University of Cambridge. SAIL aims to provide an engineer-friendly, vendor pseudocode-like language for describing instruction semantics. It is essentially a first-order imperative language, so it uses predicates which can define non-logical objects. An example sentence would be there exists X such that X is Socrates and X is a man. But SAIL also has lightweight dependent typing for numeric types and bit vector lengths, which are array data structures that compactly stores bits. These are automatically checked using Z3. The prover, not the BMW. It has been used for several papers available from the University of Cambridge SAIL website. The link is here. Given a SAIL definition, the tool will check it and generate executable emulators in C and OCaml, theorem prover definitions for Isabelle and Hoc4, and definitions to integrate with the REM tool for concurrency semantics. To introduce the features in more detail, I will now go through a simple RV64I example. The RV64I in SAIL is handwritten. We will start with some basic type synonyms. We create a type x_t for bit vectors of length 64. Then we define a type regino, which is a type synonym for the built-in type atom. The type atom is a number which is exactly equal to the type variable atom. Type variables are semantically marked with single quotes, as in ML. A constraint can be attached to this type of synonym, ensuring that it is only used when we can guarantee that its value will be between 0 and 31. SAIL supports a rich variety of numeric types, including range types, which are statistically checked. We can then define a synonym, regbits, for bits 5. We don't want to manually convert between regbits and regno all the time, so we define a function that maps between them and declare it as a cast, which allows the type checker to insert it where needed. By default, SAIL does not do any automatic casting, except between basic numeric types when safe. But to allow idioms in ISA vendor description documents, SAIL supports flexible user-defined casts. To ensure that the constraint on the regino type synonym is satisfied, we return a quantified type. Now we set up some basic architectural state. First, creating a register of type xlen_t for both the program counter, PC, and the next program counter, next PC. We define the general purpose registers as a vector of 32, xlen_t bit vectors. The dec keyword isn't important in this example, but SAIL supports two different numbering systems. We then define a getter and setter for the registers, which ensures that the 0 register is treated specially. In RISC V, register 0 is always hard-coded to be 0. Finally, we overload both the read Rx and write Wx functions as simply x. This allows us to write registers as xr equals value and read registers as value equals xr. SAIL supports flexible ad hoc overloading and has an impressive language in assignments, with the aim of allowing pseudocode-like definitions. We also give a function memr for reading memory. This function just points to a bulletin we have defined elsewhere. Note that functions in SAIL are annotated with effects. The effect system is quite basic, but indicates whether or not functions read or write registers, rreg and wreg. Read and write memory, rmem and wmem, as well as a host of other concurrency model-related effects. They also indicate whether a function throws exceptions or has other non-local control flow. The escape effect, for example. It is common when defining architecture specifications to break instruction semantics down into separate functions that handle decoding, possibly even in several stages, into custom intermediate data types and executing the decoded instructions. However, it is often desirable to group the relevant parts of these functions and data types together in one place, as they would usually be found in an architecture reference manual. To support this, SAIL supports scattered definitions. We first give types for the execute and decode functions and declare them as scattered functions, as well as the AST union. Now we provide the causes for the add immediate AST type, as well as its execute and download causes. We can define the decode and the decode causes. We can define the decode function by directly pattern matching on the bit vector representing the instruction. SAIL supports vector concatenation patterns. For example, the symbol @ is the vector concatenation operator and uses the types provided, bits 12 and reg bits, to destructure the vector in the correct way. We use the exts library function that sign extends its argument. Now we do the same thing for the load double instruction. Finally, we define the fall-through case for the decode function and end all our scattered definitions. Note that the causes in a scattered function will be matched in the order they appear in the file. The SAIL backend is written in OCaml, which is an impure functional programming language like Python. Functional languages are based on mathematical functions as opposed to procedural languages like C, which depends on flow statements such as if or for loops. The backend generates executable emulators in C and OCaml, and theorem prover definitions from the SAIL model. One of the highlights of OCaml is its parametric polymorphism and type inference, which allows operations to be written independently of the type of the elements. This is useful for architectures like RISC V and have multiple sizes of instruction, since a single operation can be used on all sizes. But how about a small example to show you a bit of OCaml? No. Wiggle the cable. Oh. The laptop's run out of battery. technical problems. We can...
Is it off? It's on. Looks like it must have gone to sleep.
I think it turned off.
Maybe you can take some questions or something.
Yeah. I mean... Pardon? Yeah, it's rebooting at the moment. I can take questions for what's gone through so far, I guess.
Your effects model just said reading memory. Does it need to say reading a particular address of memory, or is that not relevant?
So the question was, my effects model, or the sale effect model, says reading an address of memory. Does it need to say a specific address? I'm not the best expert on sale. I can put you in touch with Peter Sowell, who's the guy running Cambridge. I can give you his email afterwards, but I don't know at the moment. Any other questions?
One very simple one. About you said at the introduction that you wanted to generate things from the specification.
Yeah.
So it means that the specification needs to be written in formal language.
Yeah.
So how does that fit in?
So the question was, how does the specification being written in a formal language fit in? So SAIL is the formal language. It already generates stuff, but so that's the formal language. SAIL is. So
But let's say you have a RISC V
yeah,
definition.
yeah, in SAIL.
It's outside of SAIL.
So there'll be a RISC V definition written in the SAIL language, which will then be taken through OCaml into CGen, which I will come into in a moment. Yep. It didn't appease the presentation gods enough today, I guess. Good. Yeah.
Disassembler the source code.
Yeah.
After is the copy source code choose from compute source code is the most performance, is the GCC, or you use just the GCC, or use more software from compute source code?
So the question was, do I use more than just GCC for the source code? As opposed to LLVM or another compiler? Or didn't think I fully understand what you mean. Or,
Most performance from the compute source code.
so
Is the GCC or?
yeah, it's GCC. So the assembler uses gas and it fits into GNU tils. But should be loading up. Well, shall I carry on? Oh, I get technical support to help. So I'm going to show you an example of some OCaml. It's quite simple. It'll be a sourcing algorithm. I'm sure we've all seen them before. But it'll demonstrate the polymorphic ability. So first, it's going to define the function, the sort algorithm, and it's going to have a list input, as shown, and a list output. These will be shown by two square brackets in between, with an arrow in between. The input coming before the arrow, the output coming after the arrow. The function will prepend x onto 1 and calls the insert function. The input of the function can either be a list of integers or a list of strings. This is the polymorphic ability. So I'll carry on to CGen. At university, my final year project is to use the sale description of RISC V to generate low-level tools, namely assemblers and disassemblers. For this, I am using CGen, which is part of the GNU toolchain. CGen is an open-source CPU tools generator, which uses a framework to generate assemblers, disassemblers, and simulators. The generator is written in Scheme, a functional language like OCaml, which makes the conversion easier. CGen ports to GNU by adding a Scheme description to libopcodes, which is the GNU's library of operand codes. Libopcodes can then be used to assemble or disassemble C code using GDB and GAS, respectively. There are two steps to create an assembler and disassembler using CGen. This is first to connect CGen to GNU tils. This will allow GNU tools to look for the framework files required and generate the correct opcode files. The second step, of course, is to write the framework. To connect CGen to GNU tils, the port name is needed to be added to a list of make files and configure files. The names of the required opcode files are added too. There are 4 main files in CGen, which contain the framework and additional information to create an assembler. For RISC V, these 4 files are risc5.cpu, the main framework file. It's written in Scheme and is the focus of this project. risc5.opc. This file contains handlers for the Scheme framework. rvcpu.c. This file includes hooks written in C, which add more information about the hardware and ISA. And finally, rvcpu.h, the header file. The main file that I will be generating during this project will be risc5.cpu. the rest will be handwritten. CGen must be written in a specific order to work, which I will go through when the PowerPoint decides to work. I'll start off. Every RISC-V.cpu file or equivalent will start with include simplify.inc. This includes the instruction macros for GNU utils, which are used throughout the rest of the file. It's then followed by define arch. This function names the architecture and defines the endiness of the architecture. Define ISA is the next one, which defines the bit size of the ASA with the ISA. And then define CPU describes the CPU family, and instruction endiness again. Then define Mac. This is the function that defines the machine. Define unit. This is the function that describes the model. Every machine must have a model, and every model a unit. The unit will have 6 sections. Issue, which describes the number of operations in progress at once. Done defines the latency. State lists the variable names and mode pairs. Inputs, the units of inputs. Outputs, units of outputs. And finally, profile action, which is the RTL code for function unit modeling. Once this is done, it's followed up by a definition of P macros. These are usually used for attributes for the instructions later on. They are also used to simplify the file. This is then followed by define hardware, which defines the hardware simulated in the program. This can include the program counter and other registers. A P macro can be used to define the register names if there are many. DNF and DF are the functions that describe the instruction fields for registers and immediates. Hey. Define multi-field defines instruction fields which are made up of unconnected bit fields. Define operands defines the operands used in the instructions. It requires an instruction field. And finally, defining the instructions. This function defines the instruction format. The instructions add and sub use the same bit format. Therefore, it is simple to apply a P macro to the format. In the instructions, #B is used to define binary numbers. Multiple functions use attributes, which defines the ISA and machine of the instruction. This is shown by base ISAs. Once this file is written and the basic hooks are added to the other 3 files, make stamp followed by running a make command in GNU utils can be used to generate the assembler and disassembler. To conclude, being able to generate an assembler from the formal specification of an ISA would be very useful. The timescale for processor development could be significantly reduced if the definitions could be generated automatically from the specification. But this has proved difficult in the past. However, advances have been made with the processor specification language and the framework to generate assemblers, disassemblers, and simulators. So it's now possible. This is just a status report for my project. which is far from done, but there is a clear aim and a method. Thank you for listening. And I apologize about the technical problems. Yes? Hold on, can you speak up a bit, please?
Question about the simulator
Yep.
that's generated. Do you have any figures about the performance of the simulator? How many sections per second you can simulate?
We don't have any figures. I don't think so quite yet. Do we?
CDM simulators or interpreting simulators, they're typically in tens of megahertz most.
So
Does it have any system C bindings?
I don't think anyone's ever done that.
okay, we'll keep a note of that. So, thanks. Any other questions? Oh, sorry.
Have you considered using an FPGA for simulations?
We've looked into Verilog a bit, but I mean, I don't mind expanding into hardware programming for future projects. But, thanks. Okay. I think there's no more questions. I think that's the end. Thank you.